Today what I want to talk about is the details of how to do local alignment efficiently. And you've seen dynamic programming for global alignment. You've seen dynamic programming now for longest common subsequence problem. And today I want to show you what dynamic programming looks like for local alignment and some other variants. So let me remind you what local alignment is. Local alignment, you're given S1 and S2 of lengths n and m. And you need to find a substring alpha of S1 and beta of S2 to maximize the global alignment value, V, alpha, beta, the global alignment value you get from aligning those two strings, maximize that over all choices of substrings, of pairs of substrings. One from S1 and one from S2. So last time, just to really make this definition more concrete, last time being Wednesday when I was here, we did a kind of gross estimate of how many operations it would take if you just followed this definition literally, or the way you did your computation according to the way this definition suggested you would do it. That is, by finding all possible substrings of S1 and S2 and forming all possible pairs of substrings, and then computing V for each pair of substrings, and then looking for the best one over those. And what we found was that this would take, I guess you don't know that symbol, following the definition directly, computation of local alignment would take the number of operations proportional to n times m cubed. And that's enormous. So, huge. Okay? Not practical to do it directly that way. The other thing we talked about last time, or when I was here Wednesday, is why local alignment comes up, or some of the ways local alignment comes up. And it's sort of this picture to show you that these are two regions of high similarity, but the rest is different. And in the notes I put on the web, it discusses a number of particular ways in which local alignment arises, and also introduces the practical method. So this approach is certainly not what we want. We want something that actually works well. So the efficient solution is something called Smith-Waterman. And these are the two people, Temple Smith and Mike Waterman, two people who found an efficient way to compute local alignment. And their names are associated with not only the method, but local alignment. So if you go into the Time Logic site, you'll see a section there on using Smith-Waterman. That sort of denotes both that you're interested in local alignment and that you want to use their particular method of solution. So I'm going to start by writing down again the recurrences we had for global alignment. Okay, so we're trying to get a method, a dynamic programming approach method for local alignment, but since right now what we know how to do is global alignment, let's start there and see what it might take to convert it to a local alignment method. All right, so our definition again is that Vij is the best alignment value using the first I characters of S1 and the first J characters of S2. In the case of global alignment, what that means is you will use all of the first I characters of S1 and all of the first J characters of S2. They have to be included somehow in the alignment. They might be opposite spaces. Some of those characters, even at the end, may be opposite spaces. But they all contribute to the ultimate value, Vij. In the case of local alignment, all this means is that what we have available to work with is the first I characters of S1 and the first J characters of S2. But now you're looking for a substring of the first I characters of S1 and a substring of the first J characters of S2. Still, the overall idea of dynamic programming applies that we're going to be solving small instances of the problem, making them bigger and bigger until we finally have a solution for the entire complete problem. Okay, so what do we know for global alignment for Vij0? So this is one of the base cases. What is Vij0 in global alignment? And I'm taking the simplest version of global alignment, that is +1 for a match, -1 for mismatch, -1 for a space. So this is -I. Okay? And similarly, Vj is -j. Okay? That's global. Okay? We'll come back in a minute and see how things change for local alignment. Then in general, Vij, and again, this is going to be for global. I want you to be sure to keep these distinctions clear. Vij is the best thing you can get. It's the max over Vi -1, J-1 plus Tij. Okay, I think we've used this, but I'll make this explicit. Tij is equal to +1 if the ith character of S1 is equal to the jth character of S2. So this is the situation where we're saying, I'm definitely going to put character I of S1 opposite character J of S2, and if they're the same, I get a +1, but I get a -1 if not. Okay? All right? So that's one possibility. Another possibility is Vi-1 J. Okay, we're just going to take the first I-1 characters of S1, but we're going to use all J characters of S2. And what does that mean for the ith character? What's the ith character of S1 doing in this case? Where is it aligned? If you use up all the J characters of S2, with only the first I minus 1 characters of S1, and the ith character of S1 is sitting there opposite a space. If all you have available are the first I characters of one and the first j characters of the other. Okay, so this is a minus 1, and similarly, v I j minus 1 minus 1. So these are the four, 3 or 4 depending on how you think about it, possibilities, and these are the global alignment recurrences. And then what you do when you have an alignment problem, 0 through n, 0 through m, and you're using these recurrences, you fill in the table, let's just say row-wise. You could do it column-wise as well. Every time you're at a particular position, ij, the recurrences tell you have to look at this neighbor. That's from this one. You have to look at this neighbor. That's from that one. You have to look at that neighbor. That's from that one. And do the appropriate addition, subtraction, and comparisons. And then you'll have the value for Vij. When you finally get down to here, that's the optimal global value. Okay? All right, so everybody up to speed, remembering all of this thing? Okay, that's global alignment. So local alignment, what do we want? We want a substring from S1 and a substring from S2 whose global alignment value is the largest over any choice of substring pairs, one from S1, one from S2. So if we had that, let's just say by some magic, I happen to know where that is, and alpha is here, and beta is there. Alpha is this portion of S1, and beta is that portion of S2. Okay? And so the thing I really want to point out here if by some magic you knew that the best alpha beta pair was this one with this one, and you want the local alignment value to be the global value of alignment value of alpha and beta, okay, then actually since we always have one more row and one more column than we have characters, so here we want another row and another column. What value would you like to have in that square? You'd want a 0 to be there, okay? Because really you're not using anything of this portion. You're not using that portion of S1. You're not using that portion of S2. So you really want to say, I can just start my computation at a 0 value. So we want to allow that somehow in the recurrences. We don't want to say the value there has to be whatever we got by going forward from here. We want to be able to say, no, I'm not interested in that stuff previously. I can make that 0 if I want to. Okay? And then where would you, if you had made that 0 and you did you did the global type computation forwards, where would you see the alignment value, the local alignment value of this alpha and beta? Would it be down here? Or where would it be? It'd be there. Yeah, but where's there?
Right lower corner.
Right lower corner of this one, yeah. So this would be the local alignment value. Okay, but of course we don't know where alpha and beta is. I mean, again, if we knew where alpha and beta were, we would just throw away everything else. Essentially, that's what we're saying. make that a 0 because we'd just be doing global alignment between alpha and beta now. So that, of course, starts at 0. And we do our global alignment just as before. And then when we got down to there, that would tell us the global alignment value of alpha and beta, which is therefore the local alignment value of S1 and S2. That's if we knew alpha and beta, but we don't know necessarily where alpha and beta are. Nonetheless, the fact that you want this to be 0, meaning you want these things not to influence anything, should tell you something about these recurrent, the basis. So now we're talking about local, and the first change we make to go from global alignment to local alignment is we make both of these 0. And hopefully that's being motivated by this picture, but also just by thinking about it. This is saying, what's the best local alignment you can get when you have I characters from S1 to work with and 0 characters from S2? And it's no longer the case that you want to put all these I characters or have to put all these I characters opposite spaces. It's local alignment, so you get to pick the alpha and beta. Why would you waste any money or effort on these I characters being aligned against spaces? It's not, certainly, that's not what you want in a good alpha and beta. So these things get to be 0. This is for the first column, and this is for the first row. Or this is for the 0 column. This is for the 0. That one's for the 0 row. Okay. All right. So that's the first change we do in terms of converting global alignment to local alignment. So we'll still have one of these guys, 0, 0. It's just that now we're going to put zeros in here everywhere. Okay? That's the first thing. So that's not a big change. Now the next thing is, we still want to think recursively in the same sort of way we did before for global alignment. But let's say now we were doing global alignment, even with these zeros in here, and we get to a point where the value in here is like -5. Okay? So what did that mean? That meant that if you follow the pointers back to some 0, you're having some portion you're aligning some portion of S1 to some portion of S2, and at that alignment you're getting a negative number. Okay? But you could always just get a 0 by throwing this stuff away. Just throw away this whole business, throw away this whole prefix, this whole prefix, and you can get a 0 in there. So you should never, in the alignment values, allow a negative number. Okay? So what we do is we put, in addition to these possibilities, we put a 0 in there. Another way of thinking about that is that if you were aligning going forward from wherever you started with, and you got this sequence, this string aligned with that string and had a negative value, you can kind of hit the reset button on the alignment algorithm and turn that back to 0, essentially just saying, well, this stuff is so bad, let's just ignore it. Okay, that's certainly a legitimate possibility, since doing nothing is possible. If I take nobody from S1 and nobody from S2, I get 2 empty sequences, and they align with global alignment value 0. All right. Now let's think about the other end of these things. Again, you've been filling in the table according to these recurrences, and you get to something really good, 10 to the 6th. Big, big number there. Okay? And that corresponded to this sequence aligned with this sequence. And now everything forward starts getting bad. The end of this thing was all X's and this is all Z's. Just terrible mismatches after that point. Well, the local alignment criteria tells you you don't have to use all of these things. You don't have to use up all the characters of S1. You don't have to use up all the characters of S2. Okay? So you're permitted to simply say, that's it. I want to stop my string there and this string there. Okay? Of course, you don't know you want to stop there until you've filled out the whole table. But in terms of finding what the good alpha and beta is, whatever value here has the largest number, that should tell you the right endpoints of these two sequences. Okay, so I know what I've been saying so far is only, at best, kind of pointing you into the right intuition. It's not formal. Definitely not a complete proof by any means. In fact, what I've put in the notes, and I'm not going to do in class, is what I think is a formal proof that this is it. The famous Smith-Waterman, which is, it is a real accomplishment, but syntactically, it's almost the same as global alignment. It's just you change the bases, the base conditions to 0 here. You put this extra condition, this extra comparison in here, so now we're maximizing over these same possibilities as before, but also a 0. So if the best of these things was negative, just make it a 0. And finally, instead of taking the optimal here in this lower right-hand corner, because that would mean you're using up all of S1 and all of S2, you find the optimal by looking in the table and taking the largest value. Okay, so the optimal value is taken to be the largest number in the table. Okay? And that's, that's where you get the value from. Okay? So zeros in the 0 column, zeros in the 0 row, fill in the table according to these recurrences. Once you've filled in the table, you either keep as you're going where the largest value is, or you look back again and find it. That will tell you the right end of alpha and beta. To find the left end of alpha and beta, we always leave these pointers, the breadcrumbs of the kind that we had for global alignment. You just trace this back to the first 0 you hit. And that tells you the left end of the two sequences, and that's where you get the alpha and beta. All right, now I know, again, this shouldn't be absolutely crystal clear why it's right. I hope everybody sees the mechanics here, but the reason why this actually is right is a little bit subtle, and the formal proof of correctness is in the notes on the web that I put out last week. So if you're of that kind of mind to do so, you should read those notes, but I think it's a little too formal for this kind of class. But I do want you to see how similar this is to global alignment, because actually this is kind of a theme that, we have local here, that there are many problems you can solve efficiently by just making some small changes to the dynamic program recurrences for this basic global alignment. So let me just to see how many people are really with me at this point. We did an analysis of global alignment to see how many operations it needs if you have one string of length m and one string of length n and one string of length m. Okay, everybody remember the number of operations that we did that were needed in global alignment? What is it? Is what?
Plus R, C, R, C, and R. I think.
No, that's counting the number of alignments.
O and M.
It's what?
O.
Yeah, proportional. I'm just going to drop the actual constant number, but proportional to m times m. Okay? That was global alignment. Now, for local alignment, these are the recurrences. How many operations does local alignment require? Well, take the analysis the same way we did global alignment. At a particular position, ij, at a particular position, ij, you're looking through these possibilities. Okay? You need to look up vi minus 1j minus 1. You have to figure out what t is. You have to do that addition. That's one thing. You have to look up vi minus 1, j minus 1. You have to do that addition. You have to look up this value and do that addition. So how many operations is that? Well, we said before that was about 12 or whatever. So that's still about 12. But now, instead of taking the maximum of those 3 values, you have to take the maximum of 4 values because you have 0 in there. Okay? So if before we had 12 operations, now, I don't know, 13 operations. So some fixed and relatively small number of operations per cell. How many cells? Roughly n times m. So the total number of operations is proportional to n times m. Not much different. I mean, it's, in terms of proportionality, it's the same as what we got for global alignment. And in terms of the actual number of operations per cell, very, very close, very similar, differing by 1, maybe 2, I don't know. So on X per L, on the lengths, the sequences that we have there, or on a Lion, that's the Stanford web-based facility, or time logic, whatever sequences you give, and you once ask for global alignment, and you clock it with your watch, and then you ask for local alignment, you won't see any difference. Okay? Virtually the same running times. And so this first estimate that we did, which was quite pessimistic, which had this cube in here, which said that global alignment was going to be massively more efficient than local alignment, as if you did this local alignment by definitional, just following the definition. This is way too pessimistic because ultimately we get rid of that and this becomes practical. Okay, so I wanted to do that counting just so people were clear on the mechanics of these recurrences. Smith-Waterman remains a sort of major milestone and accomplishment in bioinformatics. The fact that local alignment can be computed as efficiently as global alignment. Maybe I should just do a full example here that might help get your intuition going better as for why these minor changes actually work. And I should say one thing. On the web last week, I put 2 notes concerning local alignment. One I called formal analysis of local alignment. It's pretty long. I don't know, 5 or 6 pages, and it has the proofs that I was mentioning. And then there's just one more smaller page called Smith-Waterman algorithm for local alignment, and it's more streamlined. And I do mention in there something about this is what you need for Lab 4. Okay, this was written last year. I didn't catch this when I put this up here on the web. Though it's not referring to Lab 4 this year. We'll probably get to this, to an exercise that uses this next lab. Well, I can tell you what it is. You take the code for Needleman-Wunsch in Perl. Okay, Needleman-Wunsch is, or Needleman we call it, in Perl. That's what does global alignment. And you convert it to a program that does local alignment. Okay? And how long do you think that should take you? You know, if you're lucky, 5 minutes. Otherwise, an hour. Right? But it shouldn't be much because it's all there. So let's just make up an example here, not too long, of one. ACAT and a cat as opposed to, ACT. And then we're going to, so this is the part this is going to be the alpha and beta. It's going to be, actually that's not good enough. Let's make another, like that. So that's going to be the alpha and beta, and then we're going to junk it up with something that tries to disguise it, like CC, TT, and then A, and a G. Okay? Those are actually pretty big. And this is going to be the 0, 0 row. Okay, so 0, 0. Okay, so I'll try to make this a little neater, but I won't succeed. Pretty big. Actually, on your next homework, I should ask you to do one of these by hand as well so you get a good intuitive feeling. How many people thought that the global alignment one that I asked you to do was just way too tedious for its value? One person. Okay. All right. So the base case here says, oh, the 0 row and 0 column, you get to put zeros in there. Okay? And a 0 in there. That's different. Now we're going to fill in the rows row by row just as before, as in global alignment. Okay, so this cell here, if this was global alignment, you would say, well, T and C are different. Okay, so this value is either 0, -1, which is a -1, or this would be a -1, and this would be a -1. So you'd be comparing -1 to -2 and seeing that -1 is the best. But now what you're doing is you're comparing -1, that comes that way, with -1, that's what comes that way, and -1 that comes that way. Now with a 0. And you want the largest. And the largest is 0. Okay? And so this is just saying, if I want the best local alignment between a string that consists of T and a string that consists of C, the best thing is to do nothing. Okay? I mean, maybe, if you think that's, if in your model, in your particular problem, that's cheating, you're not permitted to just do nothing, then you'll have to change the recurrences. But in our definition for finding the best subinterval of a string in one and subinterval of a string in the other that had high local similarity, basically this says there isn't any. Okay, so now we go over here, and again, we would compare 3 -1s with a 0, and 0 still is the best, and it's going to happen again, and it's going to happen again and again. And now when we get over to here, we finally have a negative 1 coming from there, a negative 1 coming from there, but from here we have a positive 1. And that's the best. Okay? So what is this saying? This says, if I get to use all of this and only this, and my objective is local alignment, my objective is to find the best substring of this thing, and along with a substring of this, it gives me the best global alignment. Well, it's clear the best thing to do is you just pick this as your substring, and you pick this as your substring, and it has a global alignment of 1. And so I'm just trying to point out here that formally what we've been doing by following the recurrences is exactly right in comparison to our intuition just by looking at this example. Okay, now we go over here, and what do we get? We get plus 1. Okay, so here's a little quiz. What value would you get here by looking at this case? I hear a plus 2. What else do I hear? I hear a 0. Okay. Which one's right? This is just looking at this one case coming in from here. Should it be a 0 or plus 2? It should be a 0. Okay? Because by following the recurrences, you get this value. Okay? That's the I, j minus 1. You're taking its value, which is plus 1 at the moment, and then subtracting 1. So that gives you a 0. So that's one possibility, is 0. This way should give you what? That gives you a plus 1. And this way gives you a minus 1. So the best over those three, 0, plus 1, minus 1, is a plus 1. Plus 1, and we got that way. And again, I said earlier that the way you would actually find the substring, if this was going to be your right end, is you would follow the pointer until you hit a 0. So this is one way of getting a plus 1 using all of this against this. And here's another way of getting a plus 1 using all of this with this. Okay?
After the A is a plus or is a T?
Oh, well, this is a T. This is DNA. Well, presumably. Okay, and then let's look at the value here that you get. You get, from here it would be a 0, from here it would be a negative 1, from here it would be a negative 1. And so 0 is the best one there. All right. So haven't made a lot of progress yet. Let me see if I can speed this up a bit. 0, 0, 0, 0, 0, 0, 0, plus 1. Okay. And now it's going to be plus 2. We go, that way for the plus 2, and then this would be a plus 1. Okay, and 0, 0, plus 1,
0,
0, coming that way, and then a plus 1 coming that way, and then a 0. This was a plus 1. So we got a 0 from there or there, and this is a plus 1 coming from there, and then this is a plus 1. Oops.
No. Plus 3. 3.
No, this is a 3. Okay? You get a plus 3. Formally, by looking at the recurrences, you get a plus 3 there. And where does that really come from? It means if you take the first three characters here. What's the best local alignment using the first three characters here and all of these characters? Well, it's this alpha with this beta, which gives you a +3. And you're seeing it formally by getting the +3 from here, which gets the +2 from there, which gets the 0 from there. So you follow back the pointers till you hit a 0, and you're golden. All right. +1, +1. 0. +1, right? No.
+2.
+2 from here, right? From here. And then this is a
+1.
+1, and then this is a 0, and a 0, and then a +2. Okay? All right. So now we haven't gotten any negatives yet. So this was not a great example because we would like to get some negatives after we'd gotten a lot of positives. We'd like to get something in there which is really terrible looking in the middle, and we'd get some negatives, and then we would say, oh, but with the recurrences, we'd set one of those to 0 and say, oh, reset. Yeah, question?
I was just going to say, how do you get a negative if you're always choosing? You have a 0 to choose from. You're always going to.
Well, I know. What I mean is all the other possibilities you'd be at a cell where the three possibilities were about to give you a negative, and then you'd say, no, it's better to make it a 0. Yeah. But you'd be driving down some of these numbers to where they would ultimately all just give you a negative. But we don't have that. Okay, so now the t, so this is a 0. This is tedious. It gets, especially after an all-night flight. C, okay. I'm losing my concentration here. But fill it in, and you will discover that the best one is a cat, I think we'll discover, with a CTT, or a, okay. So it's ACATT with ACTT, and you'll see the maximum value here. This will be bigger than any of the other values down here. And when you trace back the pointers, you will trace back to this as your left endpoints of the two strings. So actually, this is a good thing to ask you to try to fill in at home and make sure that that's what you end up with there. Okay, so the main point from today is that local alignment does not take you any longer than global alignment, and that it's some small changes are needed in the program to actually do the computation. Even the traceback is essentially the same, except that you have to stop when you hit a 0. You have to start at the largest value, and you have to stop when you hit a 0. Now, there was another, on X per L, if you remember, there are actually 4 different choices for style of alignment. You can do global alignment, you can do local alignment, you can do n-gap free, or you can do one string as a substring of another. Okay? N-gap free is just the alignment criteria, which says that if I have 2 sequences, 2 strings, and I have a gap that actually happens to be at the end of one or the other strings, that we don't want to count them. Okay? This actually comes up quite often, where the kind of sequence comparison, the kind of alignment you're trying to do, is the prefix of one string with the suffix of another string. Can anybody suggest an application they know of where what you're mostly interested in is trying to find a good suffix of one sequence, how it aligns with the prefix of another one? You want a large value. You want to maximize your matches minus your mismatches and so on. But in the things that hang over here before the suffix, you really don't want to penalize. And the things that hang over here at this suffix, you don't want to penalize either. Yeah?
Like primers for DNA or patient?
Possibly making primers for DNA. I'm not sure how that works myself. But anybody know anything about shotgun sequence assembly? Okay, you get all these fragments that are intended to overlap, not intended to be the same lengths. One is intended to overlap the other one. And you have to kind of figure out what's that path through those fragments where one overlaps the next one overlaps it, and so on. And this is pretty much what they do with some heuristics to speed things up, is you want to find suffix-prefix matches that are really good, and therefore you want to throw away these things. So I'll let you try to think for next time, how do you change the recurrences if you don't want to count this stuff and you don't want to count that stuff? How do you change the dynamic program so that's what you get? And you can play an Exparel and see how that actually changes what you get in practice.